Okay, so now this is lesson 8, even and odd functions and symmetry. Okay, so we're still dealing with functions. We're going to start off with something which you notice about many numbers is that some numbers are even and some numbers are odd. Okay, so we'll talk about that because you can have even and odd functions. Okay, and so here's the definition that we're going to use for an even function. Okay, a function is even if replacing x with a negative x does not actually change the function values, right? So the function actually stays the same whether you have positive or negative x's in there. Okay, and so you can kind of see that in the graph here. And also notice if you look at the graph, there's some symmetry with respect to the y-axis, right? See how the left side is a mirror image of the right side, right? Okay, there's some symmetry there. Okay, and so let's talk about this definition again. So the function values are the same whether your x's are positive or negative. Okay, so let's kind of plot that out here. Whenever, let's say, x is 2, we have that y is 0. Whenever x is negative 2, we have that y is 0. Okay, so in both instances, the y value is the same. Okay, well, what about, and I don't see any really nice points on here, but let's say that this one right here is 1.5, negative 1.5. It's not quite, but let's say it is. Notice the y value is 1, 2, 3, 4, negative 4. Okay, so when I plug in negative 1.5, I get negative 4. Positive 1.5, I change the x value. I'm still at negative 4, right? So you can actually see that the y values are staying the same, whether you have a positive or negative version of the x value. Okay, and so that's what draws out the symmetry. That means every point on the left side is going to have a matching point on the right side. That's why you see the symmetry with respect to the y-axis. Okay, so that's the definition of an even function. An odd function is similar. Notice that you change the x to a negative x. In other words, you change the sign of the x values. It does change the y values. It changes the y values by changing the sign of the y values. Okay, changing the sign of the outputs. Okay, so let's see if we can track that in this picture. Let's see. Let's go this one. I know it's not quite there, but we'll say this is at negative 1, 3. Negative 1, 3. Okay, so now let's say what happens at positive 1. What happens at positive 1? Oh, positive 1, negative 3. The y value changed its sign. The value, right, the absolute value stayed the same, but the sign changed. Okay, and that's true throughout this point right here. Let's say that's at 1, 2, 2.5. 2.5, 5. Well, then I can expect if I change the x value to negative 2.5, this graph should be located at negative 5. So let's see, here's negative 2.5. Sure enough, there is that second point. Okay, so changing the sign of the x value changes the y value as well. That would be an odd function. Okay, and you can still see there's also some symmetry there. There's symmetry with respect to the origin. Okay, and so how do I map that out? Okay, well, there's a few ways to look at it, but draw this dashed line right here, right through the middle. Okay. I don't know if I like that one, but you can still see it, right? You can see that there's this point right here. If you were to flip it around, so down and across, it ends up here. This point right here, if I were to bring it down and across, it matches here. Okay, so that's what it means to be reflected across the origin. Basically, the signs of each point change. Okay, so let's get to some problems here. Let's determine algebraically whether or not this function is even, odd, or neither. And maybe you know there's a shortcut that you can look at and identify it here. But let's say we don't know that shortcut. The definition says for even and odd, first thing I need to try to do is change x to a negative x. So I'm going to change x to a negative x in this problem and just see what happens. Okay, so notice I put that in parentheses, right? It's no longer that x that's raised to the fourth power. It's a negative x being raised to the fourth power. Okay, and then when you raise a negative to the fourth power, or any even power, the negative cancels out. Why is that, right? If I had a negative and a negative, negative and a negative, every pair will, of course, be positive. So there's two more, right? And so it turns out that if you have an even number of negatives, of course, it's going to be positive. If you have an odd number of negatives, so let's say this was x to the, or negative x to the fifth power, there'd be a positive there, there'd be a positive there. This one does not get canceled out, so the result would be negative. All right, I felt like I should probably go over that real quick. Okay, so anyway, we had an even number of negatives, so we end up with a positive. The negative cancels out completely. I'm left with positive 3x to the fourth. Compare that to the original. It's the same, right? So it turns out that changing the x to a negative x has no impact on the function. The function stays the same. The function value stayed the same. That is an even function because changing the x to a negative gave me my original function back. So that function would be considered even. Okay, let's try this one as well. So here I'm going to change x to a negative and see what happens. Of course, that means I need to change both x's. Negative 1 over x minus 3x. Okay, so now that's clearly not the same thing as the original, right? These are not the same. But it's the complete opposite, right? It's the complete negative of it. In other words, this is kind of the same thing like having negative 1x plus 3, right? You can factor that negative out. Now, this part is the same as the original. So this one is odd because I got the negative version of the original times a negative. In other words, when I change x to a negative x, I got the negative version of the original. So this function is odd. Okay, and then let's do this one here, this g of x. Change x to a negative. Okay, so changing x to a negative there, I can't just factor that negative out. It's under the square root. So it has to stay in there. So this is clearly not the same as the original. They're not the same thing, so it's not even. But it's not this, right? This would be odd, but that's not what this is. I can't just take the negative out. So it's not that, so it's not odd. So it's okay. It can be neither one. That happens, right? It's possible that you have neither even nor odd, just like you have numbers that are neither even nor odd, right? You don't think about those very often, but what would 3 over 2 be? Yeah, I've heard arguments that it's both even and odd. Okay, anyway. Now these are the same exact functions here, okay? We just algebraically determined that the top one here was even, the second one was odd, and then the last one was neither one. But remember, we did say that there's an element of symmetry, okay? And so if you can look at it and you see that there's symmetry with respect to the y-axis, right? The right side here has a matching left side. They match up exactly, right? This point here has a mirror point there, and so on. It's even. We identified that by looking at the graph and seeing the symmetry. Okay, all right, so the next one, without showing you the graph, we know that's going to be odd. Remember, odd means it's symmetric with respect to the origin. So in other words, if you imagine this dotted line that cuts across through the center, like that, either y equals x or even y equals negative x, one of those graphs. If you see that, the graph will be reflected across it. So let's see. Yep, there it is. Put that dotted line there. Kind of missed it a little bit. Try that again. A little bit better. Okay, and so you can see it there, right? This point right here, if I went down and across, it would match up with here. This point matches up with that point. This point matches up with this point, right? So there's the symmetry. You can see it there. This one is odd. Okay, and then this one here was neither. Okay, so let's check the symmetry for both. If it were even, we'd have symmetry with respect to the y-axis here. In other words, this right piece would have a matching left piece. It does not, so there's no symmetry with respect to the y-axis. So we cannot say it's even. If it were odd, it would have symmetry, we could say, with respect to the origin here. And so every point would have a matching point, so that would match up. This point here would be here. This point here, or is that 1, 2, 3, 4? No, 2, 1, 2, 3, 4, down 2 would be there. It would look like this. And I don't see that either, right? So it's not odd. Neither one. Okay, so that's two different ways you can look at this, right? And it's good to be able to look at them two different ways. Because if you look at it one way and you see that it's even, and you look at it another way and you see that it's odd, then there's some kind of, there's something going on in your thinking that's not quite right. So you can identify the problem there. All right. Now let's talk about symmetry. So this is written a little bit differently. It's the same idea, but this is not presented in the way where you deal with even and odd, okay? Or even and odd, yeah, functions. So this still has a graph though, and it's possible that there's some symmetry in the graph. So another way you could do this, if you're given the problem like this, if a function is even, or I'm sorry, if an equation gives you an even graph, all right, even, changing your x to a negative x does not actually change the problem. Okay? All right. If it's odd, changing the y to a negative y does not change the equation. Oh, not even and odd. That's why I'm getting confused. If it's symmetric with respect to the y-axis, you change the x value and see what happens. Does it change the equation? If it's symmetric with respect to the x-axis, you change the y value and see how it changes the problem, if it does at all. If it's symmetric with respect to the origin, you change both the x and the y and you see, does it change the equation? Okay, if it gives you the exact same equation or the same graph, all right, which could be a variation of the same equation, then you would say that it is symmetric with respect to the y-axis or the x-axis or the origin. Okay, and so let's test it out. You have to test these out one at a time. Is it symmetric with respect to the y-axis? Change the x to a negative and see how that changes the equation. Now, we talked about it earlier. If you raise a negative to the second power or any other even power, the negatives cancel out. So you're left with the expression without the negative. Now compare this to the original. It's exactly the same. So we would say that this equation is symmetric with respect to the y-axis. To check the x-axis, We're going to change the y value. Leave the x value alone. Okay, so 3x squared negative 4 times negative y is a positive 4y. Okay, and compare that to the original. They're definitely not the same, right? They're not even equivalent. Okay, what I mean by they're not equivalent is you could imagine that to alter the way the graph looks, you can multiply, not the graph, alter the way the function looks, multiply the left side and the right side by a -1. The graph would be exactly the same, but the equation looks different, right? But even that version of it doesn't match up. Okay, so we are not symmetric with respect to the x-axis. Okay, and then for the origin, I'll do that one here. Let me kind of box this off. Change both the x and the y and see what happens. So again, we know what happens here. That becomes a positive x squared. We know what happens here. That becomes plus 4y. Okay, I got this one again, right? I got that equation again. It's not the same as the original, so we'll say no. So this particular graph is symmetric only with respect to the y-axis. Okay, we should do another one. Let's just do this one. And then we'll see if we need to do more than that. All right, so 3x squared minus 4y squared equals 10. Let's see if we have some symmetry there. We'll start off with the x-axis. Change the, I start off with the y-axis usually, right? Yeah, y-axis. Let's do y-axis first. Change the x to a negative x. Leave y alone. Negative x squared is a positive 3x squared. Okay, let's compare that to the original. It's the same, right? So this one has symmetry with respect to the y-axis. X-axis, you leave the x alone and you change the y. Negative y squared. It's going to become positive. So notice the minus sign is going to stay, right? There's a couple ways you can think about it. This became a positive y squared. The -4 was not impacted. Another way to think about it is we have two negatives here because that's, negative squared. There's two negatives and a third negative. So that's an odd number of negatives. So you should still have a negative. Yeah, there's a couple ways to think about that. All right, equals 10. Compare that to the original. It's the same. This one is symmetric with respect to the x-axis. Okay, the origin, check them both. Negative x squared becomes just x squared. I keep putting the doggone 3. Minus 4, the y squared, negative cancels out, equals 10. Compare that one to the original. It's the same. This one's symmetric with respect to the origin as well. Okay, anyway, I'm going to go ahead and stop recording.